I'm Baria from EGS Energy. I will start a little bit slower because there is this misunderstanding generally that geothermal is not cannot be associated with Britain, but it's something in New Zealand or Iceland or somewhere else, but not in the UK. And perhaps I can persuade you that that's not the case. It's applicable to a large portion of part of the world. Now, if I right, the talk will be in roughly 3 parts. The first one is why do we want to develop this technology, and show you a little bit about it. And I'm sure you know a lot about it on energy demand, supply, and trends. A little bit to tell us why we're doing it. We're not doing it just for fundamental research, but we want to do it because we want to fill the gap that's becoming apparent. The second one is about the experience and know-how. Where are we to date on this technology? And third one is to build the first commercial plant in the UK. Now, if you see here, this is a graph produced by Shell some years ago. That's the time there, and that's the energy demand on that. And you can see the different one: coal, oil, gas, and they cumulatively plotted all the possible available of this resource over a period. And then they also produce what is a demand curve. So that's a demand curve, and that's a supply curve. And they try to evaluate what renewable energy will be required to bridge this gap. And you can see we're somewhere around here. Yeah? And as you can see, and the actual value is not important, it's the general trend that's important. And you can see as the supply and demand digresses, as usual, the market takes its normal process of increasing the value. So you can see now we're talking about 1.5 pounds or £1.50 a litre. And as this goes digressing more and more, this energy, because of energy deficiency, the price of energy is going to go up. And when Shell looked at it, all the different ones, they came to the same conclusion, and maybe I'm a little bit biased on this one, that geothermal has to pay a plant to fulfill this gap. And I can see that when we talk about 50-50, that if this trend is to be believed, that it is not just the energy prices going up. I believe there may be national conflicts. So I think politicians ought to be aware that 50-50 is very, very critical, and we really need to be able to bridge the gap that's required in the energy deficiency. Oops. Now, if you see here, I was at an IPCC meeting, and when I came out, I was quite surprised. People thinking that, as I said, geothermal is nothing to do with me, it's Iceland and so forth. And I asked a number of laypersons, what do you think about geothermal? And they said, again, here, there. And I said, but hang on a second. You are standing on Earth, and you know that as you go deeper, it gets hot. And they said, yes. But do you think we may be able to extract the heat out? Oh, that's a good idea. This is exactly what engineered geothermal system is about. Is that if you look here, this is the one I've extracted from US DOE, that this is a core and this is a crust. And you can see from here, there's enormous amount of heat at very high temperatures available. Now, in some part of the world, it's easily accessible, other parts is difficult. So if you go sufficiently deep, you should be able to get the temperature you want. And last night, I just decided to put some figures. Because stored energy in Earth is 12.6, 10 to the 12 exajoule. Exajoule is 10 to the 16. So it's a huge, I know it's mind-boggling. Even here, 1 exajoule is 2.7, 10 to the 4 gigawatt hour. So all I'm trying to say, there's a huge amount of energy that we have below, we're standing on. We need to find a way to exploit it. Geothermal is generally categorized in three sections. One is hydrothermal, which is a natural system. Then this is engineered geothermal. It started in Los Alamos in the early 70s, where nuclear scientists and rocket scientists sitting together, coffee time, thinking various things, and somebody said, hey, hold on a second, why aren't we able to extract heat below our feet? So what I was saying. And the project started there. And so the US first called it hot dry rock because there was an in-situ fluid there. Then Japanese came up, which went a slightly different angle to it. They called it hot wet rock. Then Shell came in and they wanted to call it hot fractured rock. But all this reason for variation is because the geology and particularly the petrology varies. And therefore you need to engineer a solution to the environment that you find. There is not a unique solution. You have to engineer a solution. So then we came up with the title of engineered geothermal. You fix your system to what conditions you find. And there is obviously active underground heat pumps. Now, just to give a brief on hydrothermal system, you see all these power plants, and they're all on tectonic boundaries. The crust is thin, it's easy to access. You see, like for instance here, I think there's one in Italy, Japan. So there is quite a significant amount of hydrothermal system. But when you think of a large population here and Europe, there isn't, because we are not on the crustal boundaries. But the heat is there. So we need to develop a system of extraction. And the basic model is this one. What one does is drill a borehole, schematic, to the depth you want to go where you get the right temperature. You then inject fluid under pressure and open up existing fissures. And you monitor how the fissures are opening up by seismic network, like tracking a submarine. Once you do that, then you put your second borehole and a third borehole in it. So the water goes down, cold water goes down, the water flows over these fissures, gets heated up and back to the surface. It seems simple, but the technology is much more complex. What happens is, effectively, is the interaction between the in-situ forces here and the pressure that you put in. You need to know how to maneuver this. A unit like this, say, for instance, if you go to 5 kilometers, you will get about 150 to 200 degrees, and it produces around 4 to 8 megawatt electric. But there's also, with it, a lot of thermal energy as well. In the past, when I first started, at the time the discussion was that all we want is electricity, not heat. But the equation has changed altogether because the heating cost has gone up, so thermal resource is equally important. At the discussion at the IEA, they recognize now that although hydrothermal is important, engineered geothermal is even more important, and it's got an enormous resource. Before, people were only generally giving credit to that one. Now there is a recognition that this will come, and it's very, very important. And estimates are roughly made. For hydrothermal, that's 1 terawatt electric is estimated. This is ground heat pump is 4.2 terawatts, but this is thermal. There's a difference between a thermal and an electric. It's about 10 to 1 ratio. And EGS is 4.5, but there's a discussion going on. Most of the estimate is for 5 to 6 kilometers, but there was an MIT study done on this one, and it goes up to 10 kilometers because addressed towards 2050. If we go in that direction, this will at least double, if not more. So there's a huge resource here. And this is a magma. It's a sort of a project that's being researched in Iceland to get temperature of say 350, 450 degrees centigrade. And that's a resource associated. To give you some idea of what does it mean, in 2006 the worldwide electric generation was 2.1 terawatts. So EGS is very, very large. It's not small. And these figures are available if you want, if you go to the IEA GIA website. A lot of these figures are available. To give you some idea of what if you take, for instance, a kilometer cube of rock from at 200 degrees centigrade, and you drop by 20 degrees centigrade, that's when it reaches 180 degrees centigrade, normally regarded as the reservoir is not usable. And that's because of the power plant. The power plant you design normally takes about 20 degrees efficient. So if you just assume that if you drop it by 20 degrees, that is equivalent to, if you want, in barrels or tons of oil. So you're talking about huge resource there, heat resource. That's how much energy is stored in a cubic, just 20 degrees reduction. And I was involved in the MIT study. The Department of Energy in the US wanted to evaluate what is the geothermal potential of the US and what can it do for the US. And this somebody did it for me, a schematic, is that if you assume all the resource in the US as a barrel of oil, you will find something. This is going up to 10 kilometers, and it is all in the MIT study. Most of the resource in the US is geothermal. And even if you assume, you can see here, all this roughly 2%. And even if you assume that all out of the 98%, 60% is not accessible, you will still find you can't but take note of the available resource. It's a matter of time when we'll be able to exploit it. Now, similar scenario is this is a study done, and I was involved in this one for Europe. BRGM and others sort of did this study. And these are at 160 degrees at 5 kilometers. Spain is a hotspot, and UK is here, a bit there and there. This is France, bits in Germany. The highest are Turkey, Greece, and Hungary are the prime resource. But the figure to note here, that is equivalent to, I can read, 35% of the EU consumption. So if we use this technology, you see huge resource, and we can get enormous, I think it's worth a huge amount of funds as well. So it is a resource that's waiting to be exploited. And let's look at what is in the UK. When I was in Cornwall, we did this study combined with Imperial College, and we came to the figure that the accessible resource, which means you can't put a plant everywhere, it's something 4 to 5% of the total resources used, and that will supply 10% of the electricity for 200 years. This is Southwest. And recently, studies done by SKN which shows it's not 10%, by 15%. They increased that one. And I think if you go to the same comparison of using the same parameter as the MIT study, this will increase significantly more than 20%. So we talk about huge resources within UK, but somehow UK public and government do not feel that geothermal has anything to do with the UK. And I think they're making a big mistake. Now, to move from resource to knowledge base. This is a UK program that was initiated actually it was earlier than that, but between 1998 and 1992. Because it was in Cornwall at the time, anything you had to do it locally. And this project, it was run by Campbell School of Mine at the Rosmano site, disused mining site. And the staff of 75, I think I'm there, staff of 75, and we were able, our brief was to understand the physics, to create the reservoir, develop diagnostic technique, how to evaluate it, build tools and things. And you can see here, you see normal flow log, temperature log. This is a high temperature instrument lab. So we were in that 10, 12 year, we were able to address a lot of understanding and physics associated with it. And you can see Prince Philip came there to look at the project. And it was exciting. And if I might say, it was a crown for the industry, because all the physics that we used afterwards is all developed here. When the project was terminated in 1992, I was asked to go and help establish a European project. This is a Sulzufore. It's something like 15 kilometers north of Strasbourg. It's an old oil production area. Oil is in here, it's just above the chalk. And we drilled that, and so the European site was established with the support of European Commission. European Commission knew that this is quite a big program. Most governments used to back off when it came to actually funding. So there were half a dozen European projects. The guy in the Commission, John Garnish, was able to persuade French government, British government, and German government to give up the national program and work together on this project. It actually, that was very good. And we were able to address a lot of the technical targets. One of the other things, because it was an EC funded program, it was an open project, so know-how from Los Alamos, CSM, these are Japanese projects, everything, we had lots of people working together as a team, and by doing that, the know-how filtered, not just the UK one, which is fundamental know-how, but other know-how filtered into here. And in 1997, we were able to demonstrate we could circulate it and produce heat. And that triggered off some of the commercial projects in Australia, in Germany, in Reno, and you can see all the different projects starting, except one, and that's UK. We're still trailing behind. Now I'm told if I double click this one, oops. I'll explain why the gentleman double clicks it for me. The two boreholes were put down to about 4 kilometers deep. And we were able to pump water down, go across this one and back. And the separation at the bottom was 450 meters. These are microseismic noises that emitted when we created this. Oh, you go back a bit. Can we go back a bit? There's a problem with that animation. Is it possible to go back? Oh, the video goes on. Right. This we created the first time in the world. We went to 4 kilometers, separated between the bottom at 450 meters, and we were able to inject fluid in there, and out it came. It was quite exciting because nobody had done that before. Industry came like Shell and they said they were not interested in 160-degree water on the surface. We want more than that. So one of the borehole was extended to 5 kilometers. And we created another system here. But this time the separation was 600 meters. We developed a technique of injection, 600 meters, and we were able to circulate this. Now let's see if it works. Now, this is important. This is the water that you see here. Is the water that we injected from the surface, went down 5 kilometers, across these fissures that we opened up, and back to the surface. There was no water there before. And the reason we know that was because we put traces in it, like a fluorescein. So So fluorescent goes down, up, and back. And it takes something like 2.5 days to come back. So your system is sufficiently large, and you'd expect a system like this to last 25 years. So it's not theoretical, this is a practical example. And we've done this about 2 or 3 times. So it's a technology. You can see that what you saw there is producing about 30 megawatt thermal. And that will produce about 3 to 4 megawatt electric. So it's been produced. From that one, the program, commercially funded program in Germany. There's an OMAT plant in Reno that's been, this plant is a hydrothermal system. But the same know-how that we used in ours is used to recover more heat using dry wells. And there's work done in Australia, and the work we were trying to do is EGS in UK to show that it is possible here. Double click. Now this is the plant in Germany. This is in town, in Landau, if anybody wants to. Can you put the sound up as well, please? That is in the town. You see what it is with 2 boreholes. So you put the cold water down, it goes to this fault and comes back. So this part generates about 3 to 4 megawatt electric. Then you go to secondary part, and this one is used for heating about 2,000 homes. And this is in the town, and the footprint is very, very small. The third one, what about the first commercial? Now, 2-3 years ago, we formed a company called EGS Energy. David Campton is the chairperson. I'm the technical director. Guy is the managing. And these, Andy Duke and Tony Bennett, they were the student at CSA. So we recruited them back. And Jörg is my German colleague who was did the drilling. So we got virtually all the expertise of development of this technology within the company. And the plant, we looked at various sites. It is not necessarily the best site, but what we wanted to do is to demonstrate to the public and the politician that this technology is as friendly as the Eden project. So we selected the Eden project, and that is very similar to what we've done in Landau. We're looking at a particular zone that will be 2 injection well, about 4.5 kilometers deep. It will give 160 degrees to the surface. We produce power plant and then heat the biomes. This biomes require heating during winter, and at present they're finding it as the cost of energy is going up, the cost is escalating. So we decided to go in conjunction with this project and demonstrate this is environmentally friendly. We can heat these, plus we can produce electricity. There is also a eco-town being built locally, and we're hoping to supply energy to them as well. That's the site. It's about 120 meters, 130 meters long, so we don't need, and the plant, the drilling will be up here. I didn't put the other slide where we laid out the rig and everything, but that's roughly, you can see. This is very much like in oil and gas, where you can have a borehole, and from one platform you can send the borehole in a different direction. You don't have to have lots of boreholes at different places. You can also roughly stack in the same place. We changed from previous thinking in that before, as I mentioned, electricity was only regarded, EGS development was only regarded for producing electricity. But we said no, heat is equally important. So we are combining now electricity and heat, and that produces a reasonable return on your investment. So as you can see, the Eden project, there's a discussion going on that they want to build a hotel. And that will be, and recreation, there was talk about theme parks and everything. So this will, as Cornwall, which requires some sort of a boost, this will certainly open up that area for holidays, not just through summer, but also through winter. And we held a meeting to inform public, and we had about 150 people. And there are a number of farmers there, and they said, is it possible for us to supply hot water to them? And I said, there's no reason why shouldn't. So we're hoping it'll help cash crop industry, now, one of these plants, this is not necessarily a big exploitation of EGS. This is just a very tiny demonstration plant to get public and industry and the politician recognize. I think this is our problem. They haven't recognized that we can do it here. This is why a small plant we proposed at first at Eden demonstration. But I have been talking to oil industry. I won't mention all of them, but Chevron and others. They said to me, if you can produce anything between 50 and 200 megawatt, we will be interested. Now, I had a sketch here to show how it can be done, and it can be done to produce this amount of power is not difficult to produce. So you then become a major player in able to supply electricity. So that is possible, and I've got a plan. And the other thing is sustainability. Okay, before that, where are we in terms of Eden project? We've an appropriate site has been selected. We're working in conjunction with the Eden project and Jim Schmidt. Yeah, okay. Planning permission has been obtained, design of the complete, engineering evaluation has been done, everything. We need something like 30 million required for the project. And the first well, we feel if we can get the first well down, people will change. You see, look, here it is. To do the first well, we need 12 million pounds. We got a grant from the last government of 2 million. Now we're trying to raise the 10 million. Now, quickly, the sustainability. As I showed you earlier, we did this sort of a first circulation, and then that wasn't accepted. We went deeper, and we did another one. So, in concept, if you have 3 systems like that, 1, 2, and 3, you can run one system for 25 years. That drops by 10 degrees. Then you go down and have this system for another 25 years. Then this system. And the calculations show that it takes 75 years to recover the 10 degrees. So in principle, you can go up and down forever. The heat through conduction will make this sustainable forever. You don't need to worry about it. I'm not sure the engineering problem are casing things, but it is possible to make it perpetual. There's a quick one here. This is to show CO2 emission. This is the year here. This is from coal, oil, gas. This is hydrothermal, and this is from EGS. Because it's a closed loop system, everything is circulated. There is no CO2 emission whatsoever. So it's environmentally incredibly friendly. And this is also for CCS, sequestration. There was a meeting in Oman on CCS, and Norwegian chemists have found a way of turning CO2, liquid CO2, interacting with basic rocks into permanent solid particles. But they weren't able to know, they did not know a mechanism or how to dispose of it. This is what happened in Cornwall. This is 2.5 kilometers. We pumped huge quantities of water, and this is something like 2.5, 3 kilometers below the system. And we were able to dispose of something like 1.5 million cubic meters. Now, if you use the same principle CO2, you can, in a certain stress environment, put in a basic rock, that's sort of a CO2, you shut it off, possibility that it will react with basic rock and permanently get rid of CO2. I think that's it. That's it.